Good morning, esteemed committee members, fellow colleagues, friends, and family. Welcome to my preliminary exam. My name is Dao Wang, and today I will be presenting our research, a simple yet powerful method for predicting daylighting performance using cGANs. This work was done in collaboration with Dr. Wen Place, Stephanie Li, Ruguan Liu, and Dr. Zhen Xin Hu. I'll be covering how our dimensionality reduction method simplifies daylighting simulations and how we introduce an innovative inverse process to predict window configurations from daylighting results. Let's get started. To begin, let's talk about why daylighting is so important in building design. Daylighting affects both the visual comfort of occupants and the energy efficiency of buildings. Architects aim to maximize natural light while minimize energy use for artificial lighting. Traditionally, daylighting simulations like climate-based daylighting modeling involves creating detailed 3D models and running simulations. This process, while accurate, can be very time-consuming and computationally expensive, which is where our research comes in. We aim to simplify this process without sacrificing accuracy. Now let's take a moment to introduce climate-based daylight modeling, or CBDM. CBDM is a dynamic analysis method that calculates daylight levels over time using real climate data. The key idea is that CBDM doesn't just look at daylight on a specific day or under static conditions. It takes into account the geometry of the space, the reflectancy of the interior walls, floors, and ceilings, the surrounding environment, and changing position of the sun. And also it considers different sky types and even cloud cover over the year that we are performing the simulation. This gives us a much more comprehensive view of how daylight interacts with a building. CBDM simulations rely on weather files for a specific locations. Each file provides solar and sky data, which contains direct normal radiation and diffuse horizontal radiation. Direct normal radiation refers to the solar radiation that reaches the Earth's surface directly from the sun, traveling in a straight path and measured on a surface perpendicular to the sun rays. Diffuse horizontal radiation refers to the scattered solar radiation that reaches the Earth's surface from all directions in the sky and is measured on a horizontal plane. This data essentially represent the solar radiation scattered by the atmosphere, such as clouds and air molecules. Essentially, direct daylight radiation is the focused beam sunlight, and diffuse radiation is the scattered daylight coming from the sky. Combined, this data indicates how much light a space will receive at a given time. This calculation uses a grid that represents a work plan of the space, which allows us to determine the daylight performance of that space. There's one more thing that I want to add on top of it. The weather file that we use in this kind of research comes with an hour interval of 24 hours a day, which means that for each day, you will get 24 data entries for each of the dimensions. To quantitatively assess daylight quality in a given space, various daylight simulation methods have been developed. Annual daylighting metrics are commonly used to evaluate daylight performance over the course of a year. These metrics help architects determine whether a design effectively utilizes natural light. Let's take a closer look at three key annual metrics used in this type of research: daylight autonomy, continuous daylight autonomy, and useful daylight illuminance. Daylight autonomy, or DA, is a matrix that measures the percentage of time a space receives enough daylight to meet a defined illuminance threshold. In most cases, the threshold is set to 300 lux, which is generally considered sufficient for most of the tasks. So DA tells us how often a space receives daylight levels that can above this threshold throughout the year. So for example, we have a cell in the room. Remember we said that we divide the room into a grid. So each the cell, we basically put a device there and trying to receive or calculate the daylight that has been received in a specific cell at that specific point. If it's above 300 lux, we put a yes there. And if it's under 300 lux, we put a no there. And throughout the year, for example, if we use a commonly used schedule, which is from 8 a.m. or 9 a.m. to 5 p.m., at the end of the year, we will collect all those data and check among those hours how many percentage of hours has received over 300 lux. If it is 100% of the time, right, we will put a red color here, which we will talk in a second. So DA is a straightforward measure, but doesn't take account into light levels that are slightly below the threshold. It is a binary determination. If it's above 300 lux, we put a yes. If it's under, we put a no. So it doesn't take anything under 300. So technically 299 lux is just the same as zero. So which brings us to the next matrix, continuous daylight autonomy, or CDA, improves on DA by giving partial credit to points in the room where the daylight level is below 300 lux, but still contributes to lighting. For example, if a point in a room receives 200 lux instead of required 300, CDA will still assign partial credit instead of giving a zero. This allows a more nuanced understanding of daylighting performance and recognize that some daylight is better than none, even if it doesn't meet the requirement or the threshold. And finally, we have useful daylight and luminous, or UDI. UDI goes a step further by dividing daylight into three categories. Useful daylight, which is between 100 and 3000 lux. Below useful daylight, which is less than 100 lux. And also exceeding useful daylight, which is above 3000 lux. This is especially important because it helps us identify areas that might be over-illuminated and prone to glare, right? Over-illumination doesn't mean there's a glare there, but they are highly related. So UDI gives us a more comprehensive view of how daylight behaves in a space by showing both the useful and problematic areas. These three matrices, DA, CDA, and UDI, help us quantify daylight performance in a room, giving us insight into how much natural light in the space receives and whether the light falls within the acceptable range for occupant comfort and, of course, energy efficiency. So to visualize the distribution of the daylight of the work plan, heat maps are often used. So in this research, this color bar represents the relationship between the percentage of the time an area falls within the ideal daylight range and the corresponding color. Let's see an example. So right here, you can see that on the left is the percentage of the time that the daylight in the specific cell gets to the required threshold. In this case, it's actually an UDI map. It means 94% of those hours in the year receives or falls into the 100 to 3000 lux range. All right, so 94%. And right here is 95, so it's still very red or orange-ish. But if it goes to the middle, right, because those areas are very close to the window and everything, it's 47, 39 means like 39% of the time in the year, this area falls into 100 to 3000 lux range. And it is right next to the window. So it is not hard to imagine that the rest of the times, most of the time, are over illuminated. So that's why it is having this whitish color. So this heat map helps us to understand the numeric values better. That's why it's often used. To simplify the process of getting daylight simulation results, many machine learning-based models have been developed. These models are often capable of generating daylight results very efficiently and with high accuracy. However, many machine learning-based models lack good generalizability when dealing with complicated real-world design cases. For example, many ANN-based models can only handle simple room configurations like single windows on the wall and have trouble when rooms have multiple windows or irregular shapes. One of the reasons for this limitation is that these models often use a small set of input parameters like room dimension and the window sizes to describe the space, which is not enough to capture the full complexity of the 3D environment. So for example, in this case, features or the dimensions of the data inputs are very limited. They only have few, such as the depth, the width of the room, and they have XS and all kind of other inputs to describe the location and the size of this particular window. Right, so in this research, you can only have one wall that have windows on top of it, which is not the cases for the corner rooms. And at the same time, you can have only one window on this wall, which is not the case for many of the design cases. In order to solve those limitations, deep learning methods such as conditional generative adversarial networks or cGANs have emerged as a more flexible and powerful solution. These models can learn to map input images such as room layouts or window configurations to daylighting outputs like illuminance maps. The advantage of cGANs is that they can generalize better to more complex room designs, multiple windows, and varied daylight conditions. The trade-off is that they require larger data sets and more computational resources for training. So let's take a look of a very specific model. It's called Pix2Pix. It was designed and developed by Philip and his colleagues in 2016 at UC Berkeley. It is based on conditional GAN, which is an extension of GANs specifically designed for tasks where we have paired training data. So in Pix2Pix, there are two core components reveals why it's called adversarial, right? One big part is called a generator. The model attempts to generate realistic image based on the input. And then also there's a thing called discriminator. The model evaluates the generated image, distinguish between the real image and the generated image. So the generator tries to improve its output to fool the discriminator, while the discriminator tries to get better at identifying fakes. The adversarial process helps Pix2Pix learn to map one image domain to another very effectively. And the reason why it's called adversarial is very obvious here. The generator and the discriminator, they are competing with each other. They are having this adversarial relationships. That's why the name of this model or algorithm was set. Let's take a look of some examples. So label to facade. This is very, very effective. And when it came out, we were very shocked, right, as architects in this field. So as you can see that this can do label to facade transition. You can have an input and you can have an output. You can just put literally just some squares and rectangles. And in the output, you will see a very, very realistic facade. And also black, white to colored image transition. There are still some websites using this algorithm to make money. So it's very cool. You can literally just input a black, white image, and it will give you a colorized version based on the things that have learned from the data set. And then a day to night transition. And the last one is sketch to photo. This was also very, very useful for designers. You can literally just input a sketch and it will give you a relatively good results for the real rendering. So Pix2Pix can be widely applied in fields like architecture, art, gaming, design, and even medical imaging. It provides a powerful way to transform various form of input data into useful context-specific outputs. Here's a more closer look of the model. On the left is an input, as we mentioned, just a bunch of squares that represent the facade. And in the middle, it's a ground truth, which is a real image from the real world. And on the right side is a predicted image, which is the model generated image based on the data set that has trained through. So when you're training the Pix2Pix model, you only give the model a input image and ground truth. So they will learn the mapping relationship in between. And after the training is done, you can bring in a input image like this into the model, and it will generate an image like this. So to calculate the accuracy or the ability of this model, you need to compare the ground truth and predicted image in most of the time. And that will be discussed in the evaluation process very intensively here. And therefore, during training, we provide a Pix2Pix model with a larger set of image pairs representing the input data and ground truth. So in specific example, in daylighting, we can see that on the left, it shows a floor plan which represents a 3D space, while on the right side displays a floor plan along with the simulation results. With a substantial amount of image pairs like this, the Pix2Pix learns the relationships between the input and ground truth, enabling it to make predictions based on the patterns it has learned. And of course, in real life, floor plan like this cannot provide enough information about the 3D space. So better encoding method is needed. Now let's take a look of the best like two research used Pix2Pix in this field. In the first one was his colleagues. We will include this article in the description. You can click it and read it. Their study applied cGANs to predict daylighting performance in multiple room spaces with multiple windows, which was a significant improvement over traditional ANN-based model. As you can see, the floor plan includes multiple rooms and multiple windows. They encode the floor plan into this grayscale map, which was used as an input to train the Pix2Pix-based model. The key strength of this research is its ability to handle more complex rooms configurations, including multiple rooms and windows, using a relatively simple encoding method. Whose team project the room layout into a grid, first of all, and then calculate the Manhattan distance of each of those cells to the adjacent windows. As you can see right here, in those cells, there's a number. And if this cell in the grid is very close to this window, it will have a low number. If it's very far, it will have a higher value. And if it's under the wall, which cannot get any of those daylight, it will get a 0. So using this kind of relationship or this kind of method, they encode this floor plan into the encoded image. Again, the reason they cannot just input this floor plan is because sometimes those line weights are very light. It's not enough information embedded into this model to train the Pix2Pix. Again, Pix2Pix is a 256 by 256 image, and you need some heavy input there to train the model, so the model have enough understanding. Some line weights sometimes can be ignored or just dismissed during the training process or during the transition process. So some image like this is needed. His team projected the room layout right on the grid, and they got this kind of grayscale map. And then they will use this as input. And of course, the daylighting simulation results for this specific room will be used at the output. So this model allows for efficient daylighting prediction across different spaces. However, there are some important limitations. The model is restricted to windows with constant height and cell height. And the underlying reason of this limitation is that it tries to use Manhattan distance to capture the information of the windows. And that is not enough, right? You cannot just describe the height and cell height of this window with just a distance calculation on basically a 2D plan. So this model training data only introduce rooms with fixed ceiling heights, window heights, and cell heights, which limits its generalizability. Overall, He's research made significant contribution, but its limitations are still very obvious. Now let's look at Lee's research, which introduced a multi-model approach to daylighting prediction. One of the key strengths of this research is its use of multi-model inputs. Lee's team contributed a method that combined both 2D tensors, which represent the locations and shapes of the windows, and 1D tensors, which capture additional information like surface reflectance, window transmittancy, and environmental conditions like solar radiation into their model. This approach provides a more detailed and accurate representation of how daylight enters and behaves in a room. The solid angle encoding method is particularly effective in capturing the shapes and locations of the windows on the wall. However, this method has some limitations. The encoding process is very time consuming. Imagine you have to divide this space into grid and then calculate the solid angles between the grid and each of the windows next to it. That's a lot of calculation. Meanwhile, in order to generate a grayscale like this using solid angle, a 3D model is necessary. And building this 3D model is very time consuming and labor intensive. So in general, just the encoding process, right? After you have the 3D model ready, The encoding process can take, on average, 7.2 seconds when they were training the model. So furthermore, this research focused on predicting specific illuminance distribution at a single point in time, rather than assessing annual daylight performance, limiting its ability in simulations that require long-term predictions. Lastly, like He's research, Lee's model was trained on room with uniform ceiling height and reducing its generalizability to spaces where more varied design are founded. So building on the research conducted by He and Lee's team, the primary objective of this study is to develop a dimensionality reduction method that simplifies daylight prediction. We also introduce an inverse process, which allows us to predict window configurations based on desired daylight results. This is a major innovation because it helps architects prioritize daylighting during the design phase. We have also designed an efficient and a more reliable, accurate evaluation method to isolate relevant data, improving its evaluation accuracy. Here's our workflow diagram, which consists of data generation, processing, model training, and evaluation. At the core of this research is our dimensionality reduction method. I want to specifically say that the terminology dimensionality reduction used here is different from the concept that commonly used in computer science, especially in CV, computer vision. This is not a method like PCA, which trying to really reduce the dimensions of the data and everything, but it is rather a method that turns 3D information into 2D. So traditionally, pix-to-pix based models mentioned in the literature review rely on detailed 3D model, which take a lot of time to create and process. Our method simplify this by unfolding a 3D room into a 2D image. As you can see here, the 2D image retains key information about the room, including window dimensions and their locations on the wall, room dimensions, room directions, right? This is facing the north here, and surface reflectancy, and even visible transmittancy of the glass. For example, white walls represent high reflectancy, while black walls represent low reflectancies. The simple encoding process allows us to retain key information needed for accurate daylight predictions while using a 2D format that works with pix-to-pix. So again, pix-to-pix can only take 2D images. That's why the previous research and our research tries our best to turn the 3D information into 2D. They use grayscale map transition, and we just using this dimensionality reduction method. By simplifying the process in this way, we make daylight prediction faster and more accessible since the users can just draw their 2D encoded maps instead of building a 3D model first. Our data generation process follows 6 steps: space generation, random openings, and then we will bring this model, 3D model, into our dimensionality reduction method to turn this into a grayscale map. And at the same time, we will send this 3D model along with other inputs, such as reflectancies of the surfaces, transmittancy of the windows, and also the schedule that we used into the radiance, which will run the simulation results for us in different matrix, DA, CDA, UDI, UDI low, and UDI up. And then we will generate those image pairs based on the output here and the output here. And of course, you can see that there are directions in this image pairs. The up is facing the north. So then we will use those image pairs to train our pix-to-pix model. Here is key parameters we used to generate our data set. We varied the room width, depth, and ceiling height to reflect common room sizes in Raleigh. We introduced different window configurations. Room can have up to 8 windows on just one wall, and each room can have 1 or 2 walls that have openings. For the 2 wall cases, it just represents the corner rooms, right? In your corner room, you can have multiple walls that have windows on top of it. And the variety ensures our model can generalize well and handle different types of real-world spaces. You can see that the width can vary from 8 feet to 18 feet. Depth can vary from 8 feet to 24 feet. Ceiling height can vary from 8 feet to 12 feet. This is an example or a sample of raw data from the dataset, which represents a space with a width of 16 feet and a depth of 18 feet. A 16 by 18 sensor grid was created to capture the daylight information projected on the target plane. The raw data includes the input and the simulation results of DA, CDA, UDI, UDI low, as I mentioned, which represents the percentage of time the space received daylight below the 100 lux threshold, and UDI up, representing the percentage of time the space record daylight above the upper threshold, in our case, 3000 lux. Using the raw data, which contains extensive information, we create training pairs for the pix-to-pix space model focused on different annual daylight metrics, such as daylight autonomy, as shown on this slide, continuous daylight autonomy, and UDI. As you can see, many cells in UDI results display yellow to white color, indicating that those areas receive ideal daylight only 20 to 60% of the time. Given their proximity to the larger glazing, it is evident that these areas are over-illuminated. Since the dataset are all done, we were ready to train our model. We trained our pix-to-pix models using TensorFlow on a machine equipped with RTX 2070 GPU. Each model took about 10.5 hours to train, running for 500,000 steps. We trained the model with 4,500 images pairs and tested them on a separate set of 500 samples. In this table, you can see that the key parameters were used in this training, such as image size, batch size, and learning rate. In pix-to-pix, one epoch represents a full pass where the model has seen every image in their training dataset one time. The number of epochs that equivalent to the 500,000 steps is about 111, which is a reasonable number in this type of training process. To evaluate the pix-to-pix model, three metrics are commonly used: SSIM, PSNR, and MSE. SSIM, or Structure Similarity Index, range from 0 to 1. It measures how structural similarity between two images are. A value closer to 1 means a better match between the predicted and true images. Capturing luminance, contrast, and structure, PSNR, or peaked signal-to-noise ratio, is measured in decibels. It is generally ranged from 20 to 40, means higher values means better quality and less noise in the image. Finally, MSE, or mean squared error, measures how much errors there is between the predicted and actual image. Lower value indicates more accurate predictions. Each of those metrics give us a different perspective of how well our model performance is. And of course, SSIM and PSNR is higher is better, and MSE is lower is better. As you can see, this image pairs from the research conducted by Ms. Lee and her colleagues. While there are some difference between the ground truth and the predicted image, as shown here, right? This red dots is right in the ground truth, but it's almost disappeared in the predicted image. But according to their evaluation, the SSIM is still a 0.911, which is extremely high. And we will try to understand why this happened. It shouldn't be this high if you can visually see a lot of differences like this. So the reason behind this exceptionally high performance is that the research compares the entire image, including the white background between the ground truth and the predicted image. The background here is irrelevant information, and including it artificially inflates the SSIM value. As a result, the SSIM score for this image pair is 0.911, which is disproportionately high. To evaluate the performance of our model, we used the matrix SSIM, PSNR, and MSE. SSIM is particularly important for this task because it measures how well the predicted images capture the structure of the real ones. This figure shows the workflow for evaluating model performance, emphasizing the use of alpha channel by isolating the relevant daylighting areas and excluding background. It ensures accurate comparisons between the predicted and ground truth. It ensures accurate comparisons between predictions and ground truth, preventing inflated SSIM and PSNR values. This method provides a more precise evaluation than previous approaches. So let's take a closer look of this workflow. After you have the predicted image, and of course you have the ground truth from radiance at the beginning, you are going to send both ground truth and predicted predicted image to the alpha channel, the alpha channel will get rid of all the background image. Although it is showing white background here, but in the actual comparison, those pixels are all removed already, and only those colored ones will be compared. And in this particular case, the SSIM is particular high, is 0.698. And that is, I think, the best case in our research. You can see that those two images looks quite similar, but still the SSIM is far below 0.9. As commonly known, the performance of most deep learning models improve with increasing training steps until overfitting. In order to find the optimal training steps, this research tested the prediction accuracies of models with different training steps. As shown in this figure, the performance of the UDI model was evaluating use different metrics across different training steps. The bottom figures isolate the accuracy of the model with more than 200,000 steps, which gives us a closer look of the relationships between the accuracy and the training step. It is obvious that when the training steps increase, the performance of the model gets better. In 3 cases, the best performance were all recorded when the training steps was 480,000. You better visualize the accuracy of the models. We have provided a few examples of our prediction result with an SSIM of 0.627, which represents the average performance of our model after 480,000 training steps. As I mentioned here, in the UDI model, the best performance was recorded as at 480,000 steps. And in that particular model, the SSIM result was 0.627. So we're just trying to give you some examples of what does 0.627 mean in our prediction. And as you can see that the predicted image looks very similar to the ground truth, although there are some variations over here and here. But you can see that even the corner details and also the overall trend has been well captured. Same as this example. This one also, the combined effects of those windows on the corners are formed in both predicted and ground truth. Again, variance does exist, but in general, I think this result is good enough. Same here. The combined effects of those windows and everything has been well recorded. Same in this case, this case, this case, and also this case. So the model's performance appears much better when background information is included when using the evaluation method from the previous research, right? They don't use the alpha channel and they keep all the information, including the background. So this evaluation process used in the previous research could be misleading as it inflates in SSIM value. For instance, without including the alpha channel, the SSIM value reaches 0.955 after just 200,000 steps. In this research, particular, the background to foreground ratio is very high compared with previous research, which is 10.6 to 1, meaning that only 9.4% of the image contains actual daylighting data. This larger background skews the result and the increase time required for evaluation by about 10 times. So our case without including the alpha channel could be even more extreme than the previous cases, since their real result might consist more percentage in their data. Now let's talk about the inverse process. This allows us to predict window configurations based on the desired daylight results. As you can see here, we are using the daylight result in the specific rooms with specific dimensions and the directions as input. And the output is this result with openings that can result in this daylight performance. So an architect could input their target daylight EMAP first, and then our model could suggest the optimal window placements to achieve those results. This is especially useful for projects that prioritize daylighting performance. Here is an evaluation method for the inverse model. Instead of directly compare the predicted image, which is the image here, and the ground truth, since the different window configurations can produce similar daylighting results, the evaluation process for this inverse model involves multi-step verification. So first, the predicted window configurations are fed into the trend opening to daylighting model, and then the daylighting results was generated from the predicted openings compared with the original input daylighting performance. And then the results were compared after the image pairs have been isolated by the alpha channel. In this case, we got 0.673. So again, the reason we just don't simply compare the predicted image with the ground truth is because different window configurations can sometimes result in very, very similar or even the same daylighting performance result. That's why we have to feed this into the pix2pix model first to get this daylighting result and compare with the original input. Here are some examples of the best and the worst predictions made by the UDI model. On the left, we have the best predictions, which tend to be for rooms with larger windows, has more numbers of openings and facing the cardinal directions. On the right, you can see that the worst predictions, typically for rooms with fewer, smaller windows and facing non-cardinal directions. The best and worst predicted samples generated by the inverse prediction models can be seen on this slide. These results share many similarities with the results of the UDI prediction model. For example, the inverse model is also very sensitive to rotation angles, tending to perform much better on samples facing the cardinal directions. And the worst predicted image generated by the inverse model tend to face non-cardinal directions. Similar to UDI prediction models, this may be because of the daylighting conditions for rooms facing non-cardinal directions are more complex, make it difficult for the pix2pix based model to capture the relationship between the geometric features and daylight performance heat maps. For the best predicted samples generated by the inverse model, the samples often contain large overall glazing areas, similar to the best predicted image for the UDI prediction model. However, the number of windows doesn't play as big of a role here, since many of the worst predicted samples generated by the inverse model also contains numerous windows, and the overall opening areas are large, which is different from the UDI prediction model's worst results. So, as you can see that in 7 of those 10 samples here in the worst predictions, they only have one window and those windows are small. This reveals the limitation of this UDI model is that it cannot predict well for the rooms with small windows and a limited amount of windows. We will discuss this right here. This slide here illustrates performance difference among daylight prediction models. The random openings algorithm used in this research to generate the data set ensures that each training sample has at least one window, yet 10 inputs here has no windows at all. As a result, all 3 models should predict blue areas all across the work plan. Because we don't have windows, they shouldn't record any daylight, and at the end of the day, it should be blue, right? However, only DA model correctly predicted this, while the CDA and UDI model produce completely wrong results. This discrepancy may stem from the model's algorithm. The DA model uses binary determination to assess daylight, effectively associate the small windows with the low light levels, as reflected in the training data. In contrast, the more complex CDA and UDI algorithm doesn't constantly record 0 on the work plan, leading to their poor performance for windowless rooms. For UDI, it is very hard to record something that is 0 because the threshold is much lower, it's 100 lux. And same for CDA. It is very hard to record a 0, almost impossible, unless that specific area really record a 0. Because otherwise, even it's just a 1 lux, we'll get 1/300 points assigned to that specific cell. So 0 is very, very hard to be seen in CDA model. And that is why in a lot of UDI worst predicted results has very small windows, because they just cannot handle things like this very well due to the nature of this data set. In order to solve this in the future, we will include more samples that has small windows. Now let's talk about the efficiency and training time. Running a traditional CBDM simulation result takes about 15 seconds on the machine used in this research, while making a similar prediction only takes about 0.3 seconds in the machine used to train the pix2pix based model. However, the amount of time used in training cannot just be ignored. Using CPU to train the pix2pix model with 500,000 steps, 450 data samples, and with batch size of 1 took about 10 hours. This means that every 1,000 steps takes about 70 seconds to train. The CPU to train this model took much more time. With every 1,000 steps of training takes about 450 seconds, making the GPU is about 7 times more efficient than the CPU. Meanwhile, due to the simplicity of the dimensionality reduction method used in this research, the dimensionality reduction process is also very efficient. As mentioned, generating an encoded map used in this research doesn't require a 3D model, unlike the methods required on the other research. Simple digital sketch tools can do the work, which also saves time compared with other dimensionality reduction and encoding methods. Implementing a user interface based on these trained models is a logical next step to bring this technology into widespread use. As shown in this slide, this interface consists three sections. On the left is the parameter input section, where users can choose from drop-downs, scroll bars, etc., to set up inputs that generate the space for the annual daylight simulation. The middle section displays a generated 2D map representing the spaces based on the input parameters. And the users can also upload their own encoded maps creating using different software such as Photoshop. The right section shows the daylighting results, allowing users to view them in real time. The example of this user interface including result can be seen in this slide. Our research demonstrates that cGAN-based models can effectively predict annual daylight results with high accuracy, even when handling complex geometrical variations. The innovative dimensionality reduction method simplifies the prediction process, while the inverse prediction models provide new opportunities for daylight-centered design, yet limitations do exist, such as a model's reliance on Rayleigh-specific weather data and their inability to handle complex room shapes, multiple room scenarios, the applications of shading devices, dynamic schedule, and etc. Some limitations can be addressed by updating the dimensionality reduction method, such as resolving the multi-room constraints as shown in this figure. Other limitations require more creative solutions, which will be explored in the future research. In the following research, we aim to expand our model to handle rooms with more complex shapes and irregular window shapes, making it applicable to more complex real-world spaces. Additionally, we plan to improve the generalizability across different locations and operational schedules, enhancing its flexibility in various climate and building use. By incorporating surface properties, shading devices, and the material transmittancy, we can increase the generalizability of our models. Finally, we are exploring predictions for multi-room configurations and complex floor plans to broaden the model's use in larger architectural projects. Thank you so much for your attention, and please leave any comments below if you have any questions. Thank you.